The question we have here is, what are the magnitude and location of the resultant of a uniform and triangular distributed loads? So let's apply the theory based on calculus to two simple distributions, namely the uniformly distributed load and the triangularly distributed load, to see what we get. So this is what we have. The magnitude of F is the area under the distributed load diagram, which would be omega naught multiplied by L, omega naught multiplied by L. As far as the location goes, the resultant force F acts at the centroid of this rectangular area, which is going to be found to be exactly in the middle of this length right there. Since we haven't treated the topic of centroid in this course yet, let's go through some steps here. So from this equation where we equate the moments of the resultant force with the resultant force calculated by calculus, we get this expression for x naught, right? So x naught is the location of the resultant force measured from this point right there. So I'm going to step by step expand this. We know the resultant force F is omega naught times L, right? And within the integral we have x multiplied by omega. Omega is a constant omega naught, so we'll use omega naught for omega times dx. Since omega naught is a constant, it could be pulled out of the integral, so that's exactly what I have done over here. And over here we are integrating, as we go from here to here, we are integrating x, and if you recall from your calculus, integral of x is x squared over 2. So grouping this 2 with this, the application of the limits to x squared makes this x2 to the power of 2 minus x1 to the power of 2. I'm sure you have learned this formula somewhere in your math course, right? A squared minus b squared equals a minus b times a plus b. So that's what I have applied in order to come to this step from this step. Then we recognize that x2 minus x1 is actually this big L right there. And x1 plus x2 divided by 2 is going to be exactly in the middle, right? Average of the 2 is going to be exactly in the middle. So this quantity is actually 2 times x1 plus L over 2. Now simplifying everything, we get this quantity for x naught. So x naught is x1, which is this distance right there, plus L over 2, right? L over 2. So you can see the resultant force is right in the middle of this length from this point to this point. Now let's consider the triangular distribution. For simplicity, I'm going to put my triangular distribution starting from the beginning of this beam. The length of the triangular distribution is capital L. The magnitude of the intensity of the distributed load at the end is omega naught. Our x-coordinates start from the beginning of the beam right here, and the point load representing the distributed load is F, and it acts at a distance x naught from the left end. Our theory says the magnitude of F is the area under the distributed load diagram. So we have simply a triangle. The area of the triangle is half times the base times the height, right? So half times L times omega naught. So that's what I have here. And this is the expression for the location of F. First we substitute this for F over here. So that's how I got this one. To expand the terms inside the integral, I need to express omega, right? Omega here is the omega at any x. So I need to express that as a function of x first. So we do this by using the principle of similar triangles. So if I take this little triangle right there, all right, and this little triangle is similar to this big triangle, all right, and therefore the ratios of the corresponding sides must be constant. So in other words, omega x over x must be equal to omega naught over L. So that's what I have here. So simplifying this, we get this expression for omega at any x. Omega x equals omega naught over L times x. So I bring this and substitute in here. Now we recognize that omega naught and L are constant, so that they could be pulled out of the integral. So that's what I have done over here. Integrating x squared, I get x cubed over 3. Now applying the limits and simplifying it, we get 2/3 L. In other words, the point load F acts at 2/3 L from this point right there. So if I were to consider this as the vertex of this triangle and this as the base, right? So the distance to F is 2/3 from the vertex, 2/3 of the height of the triangle. And obviously if I were to measure it from here, that will be 1/3 of L.